Hi, my name is Lojze Žust and I'm excited to be here today to talk to you about temporal context for robust maritime obstacle detection. Unmanned surface vehicles, or USVs, are robotic boats which have many potential applications, ranging from small scale, such as automated trash cleanup, to large scale, such as ferry transport and cargo shipping. To enable full autonomy of such boats, accurate and robust obstacle detection is required. Specifically, we focus on RGB-based obstacle detection, as cameras are relatively affordable sensors which have seen massive success across various different domains of computer vision. Currently, a common approach to detect obstacles in maritime environments is by using semantic segmentation methods. These methods classify the pixels of the input image into three categories: sky, obstacles, and water. However, the maritime domain presents unique challenges that are not common in other fields. Specifically, the water surface is unique and very dynamic in nature. Due to the waving of the water, the appearance of the surface changes rapidly with time. Furthermore, the water surface is highly reflective, resulting in a large amount of reflections and object mirroring, which often appears very visually similar to obstacles. For this reason, current state-of-the-art approaches for the maritime domain struggle to generalize and often produce many false positive obstacle detections, especially on regions with reflections, as can be seen in these examples. We observe that when we only look at a single frame of the sequence, it is generally quite difficult to discriminate between reflections of objects and actual objects. However, this becomes much easier with the addition of temporal context from previous frames of the sequence, and we can clearly see that the bottom patch represents water and the top patch represents a static obstacle. Some existing works in video semantic segmentation incorporate the temporal context using attention-based aggregation of features from semantically similar regions in previous frames. However, we believe that local texture changes are much more important for detecting reflections, and instead propose the use of 3D convolutions to capture the high-frequency local texture changes that are characteristic of reflections. With this idea, we present a novel temporal context network, Wasser-T. First, the target frame and the preceding context frames are passed through a shared encoder to extract the frame-wise features. The features are further embedded with a simple convolution to reduce the dimensionality. Then, the embedded features of all the frames are stacked together into a temporal feature volume, and a 3D convolutional layer is used to extract the temporal context from the feature volume. Finally, the resulting temporal context features are concatenated with the target frame feature embeddings and passed to the decoder, which produces the final predictions. The encoder and decoder modules are modeled after Wasser, which is an established maritime obstacle segmentation method. Note also that during test time, the feature extraction of context frames is not required. Because frames are received sequentially during test time, we can store the feature embeddings of preceding frames in memory, drastically reducing the required processing time. Current maritime segmentation datasets lack the temporal context for each frame, which is required for training of temporal methods. We thus extend the established training dataset master with preceding context frames for each annotated frame. Furthermore, the datasets lack variety, and contain relatively few examples of reflections. We thus extend the dataset and include over 150 additional examples, which have been specifically selected to capture the variety of reflections. We evaluate our trained method on the Maritime Obstacle Detection Benchmark MODS, which measures the performance in terms of obstacle detection F1 score. Values in parentheses denote the performance inside the danger zone, which is the most critical 15-meter large area in front of the boat. We find that WASR-T is able to harness the additional examples of reflections much better than the single-frame methods, and achieves state-of-the-art performance. Our method also outperforms existing temporal methods, especially inside the danger zone. Qualitative analysis reveals that the performance gains are largely due to the reduction of the number of false positive detections on reflections and glitter. To summarize, we presented WASR-T, a novel temporal context network for maritime obstacle segmentation. WASR-T is able to model the temporal texture changes and learn the temporal characteristics of reflections. The predictions of WASR-T are also more temporally consistent compared to single-frame methods. The code and all the data used in this work is available on GitHub. If you are interested in learning more, feel free to contact me or visit us at the poster session. Thank you.